Addressing energy storage limitations in intermittent renewable energy, the role of compressed air in energy storage. My name's Matthew.
I'm Peter.
Isaiah.
And I'm Upkar, and I'll be introducing our challenge. And as society advances their attention towards the environment and climate change, the importance of renewable energy is growing, as seen in the figure here. Renewable energy can greatly reduce the damage done to the environment. But the issue is that renewable energy sources, such as solar and wind, have a major drawback in that they are intermittent energy sources. This means they have an unpredictable output based on weather conditions and climate, which makes power plants and operate at less than desirable efficiencies. This can result in supply of energy being low when needed, such as in winter. The question becomes, how do we solve this issue? At first, someone might suggest looking for alternative energy sources, but this can only solve the issue in the short term. Going back to fossil fuels just aggravates the issue of climate change and results in the same problem. Others might suggest nuclear energy, which is clean energy. However, nuclear energy is not renewable and limited by materials suitable for fission like uranium and radioactive material. Other sources such as hydropower and geothermal plants are too reliant on geographic conditions and may impact Earth's environment in other ways, such as disturbing ocean flow. The solution we have chosen to solve this issue is energy storing, more specifically compressed air energy storage. It's an emerging technology in the energy sector, a method of withholding energy until the energy is needed. This is a major focus in upcoming years to optimize renewable energy generation and would greatly progress society's efforts to net zero global emissions. The problem statement we came up with is the intermittent nature of renewable energy sources creates great instability and inefficiencies, while existing storage solutions have limitations in scalability and cost. Compressed air energy storage presents a promising alternative. The purpose of this report is to give the information about the current problems regarding renewable energy generation, give some information about the emerging technology of CAES that we believe has great potential for innovation that future engineers can capitalize on.
Compressed air energy storage is an emerging energy storage technology that stores electricity by compressing air to very high pressures and storing it underground. It can be stored underground through many mediums, such as storage tanks or in already depleted natural gas reservoirs. After the compressed air is stored, it can be converted back into electricity by releasing the air that's stored underground. In doing this, the air is released and heated, which leads to its expansion, which is used to generate electricity through turbines. This works similarly to hydro storage, which leads to the question of why compressed air energy storage is such a promising technology. Compressed air energy storage poses many benefits over other forms of energy storage, as it is extremely cost-effective, extremely easy to scale up, and is very flexible, having many different varieties. There are three main types of compressed air energy storage systems, with diabatic compressed air energy storage being the most prevalent today. Diabatic compressed air energy storage uses electricity to store compressed air underground, which can then be converted back into electricity. The key factor is looking at the process of converting the compressed air back into electricity, as diabatic systems require external sources of energy to heat up the air before its release, which increases the total output of energy. Another important version of compressed air energy storage is adiabatic storage, where diabatic systems are external sources of energy to reheat the air before its release. Adiabatic systems instead save energy generated from the compression phase and use it in the heating process. This eliminates the need for renewable energy sources or external sources of energy, which increases efficiency. The third and final type of compressed air energy storage system is isothermal storage. The key difference that differentiates isothermal is the fact that during the compression and expansion phases, it will keep the temperature at a constant level, which will reduce the amount of energy lost. The biggest limitation with this specific technology is that it is very difficult to implement on a large scale due to the difficulties in managing heat transfer throughout the system.
Now, let's look at the main advantages of compressed air energy storages. First, it is eco-friendly. It doesn't rely on rare earth metals or toxic chemicals, unlike battery systems. Secondly, it is cost-effective at a large scale. It is cheaper to produce at a cost per unit area. Another big plus is high scalability. You can often use existing geological formations like salt caverns, which keep the cost for infrastructure lower. It can also release energy quickly, which helps stabilize the grid when demand suddenly spikes. Finally, it allows for long-term storage, which makes it especially valuable for renewable energy like wind and solar, which we may need for a long period of time. However, CAES does have some important limitations. Its overall efficiency tends to be lower than the lithium-ion batteries, which can exceed 90%. Then there are geological constraints. If suitable caverns or reservoir aren't available, creating them could be very expensive. Another issue is heat management. The compression and expansion process can lose energy if heat is not properly captured. So while CAES works great in right setting, it's always ideal for the location on scale to be properly managed. Despite these challenges, ongoing research is aiming to improve the efficiency and reduce reliance on specific geological features.
The CAS method offers lower costs compared to other methods when geological conditions are favorable, such as caves or abandoned mines, and is able to convert energy back with an efficiency of around 70% under the most ideal conditions and technology. While it has some limitations in terms of efficiency and local geography, they can be surpassed, leaving this emerging technology to have a bright future ahead. In terms of innovation, there are several possibilities. The inclusion of thermal management systems, which is by creating a mixed energy storage system by combining CAES with thermal energy storage, allows for a more effective heat loss reduction. Combining thermal energy managed systems allows for an increase in both efficiency and energy density. Using large artificial tanks or above ground tanks, which can remove the need for caves while also making it more costly. In addition, the future developments of CAES systems is also being done around different places in the world, where smaller or even mobile CAES systems are being deployed, demonstrating the potential flexibility of the solution. The first station using an underground compressed energy storage system is a reservoir that is operated in 1978 in Germany, outputting 290 megawatts for 2 hours. The second one was built in 1991 in Alabama with 110 megawatts of output. Canada has 2 operating compressed energy storage systems in Ontario with a total capacity of 2.4 megawatts. And even in the last decade, several more projects have been initiated in the US with a range of 175 to 350 megawatts. As such, we believe the future prospects of CAES energy systems is very bright.
In conclusion, compressed air energy storage is a promising energy storage technology. While it has certain limitations, the continuous advancements in its technology allows for improvements in efficiency through its integration into the power grid. One of the key aspects of compressed air energy storage is its ability to store large quantities of energy at a much lower cost than other competing emerging technologies. Unlike other competing systems, compressed air energy storage thrives in its ability to be implemented in many different geological areas as it has few constraints. Despite all of the benefits and strengths of compressed air energy storage, it also faces certain limitations, such as its overall lower efficiency. A hybrid approach would be the key to improving performance to make this system viable for future implementation. Looking to the future, a continued interest in compressed air energy storage, as well as a steady flow of funding and bright minds, will all be pivotal in making this technology a mainstream energy solution. With improvements in efficiency and cost effectiveness, compressed air energy storage can be a key aspect in the transition to renewable energy sources. On the following slides are listed the references, and thank you for listening to our presentation.